Good afternoon, everybody. This is the last tutorial of the day in 211. I'm here to present Tennessee with his talk on applied data science in Python.
That's right. If I'd worked out applied diet science, I'd be making a lot more money. Okay, so yeah, I'm here to talk about applied data science, and it's a tutorial, which means that it's at least optionally hands-on. There is a bunch of stuff I'm going to speak to, so if you don't want to follow through on your own machine, that's fine. You can just listen. And this is what tutorials are normally like for me. There's people who make it, there's people who don't, there's falling over, there's me falling over, there's you falling over. So what I'm going to do is explicitly represent the falling over phase at the beginning, so that everyone can spend a bit of time just getting their machines up to scratch, and I can provide a bit of tech support for a few minutes, and we can all sort of help each other. And then from then on, you can either do the exercises along the way or just sit back and just have a nice listen. So basically, you clone this repository and you run that shell script and everything works. There's no error messages. It's just all perfect. So that happened for me at least once on my machine. So it's been comprehensively tested. So who's already done this? No one. Okay, who's going to give it a go now? Okay, I've got a few people. All right. So what I'll do is anyone who runs into any kind of issue at all, which obviously won't happen, just stick up your hand and I'll walk around and we'll try and do a bit of troubleshooting for about 20 minutes, because I think the goal here is to teach you enough to be dangerous. It's not to teach you how to do it properly. That takes much longer. We just want to give you the tools to make terrible mistakes and achieve things you couldn't achieve beforehand. So I'm just going to generally do a bit of speaking that you can tune in or out of, so that the people who are installing things don't fall behind the presentation. So we're just waiting a bit. But before we set up, I did take some questions from a few people who sort of dialed in and said, look, I'm curious to hear about this in your presentation. And the ones that are represented explicitly, I'm like, yep, I'll cover it. But these are a few things that perhaps don't have their own slide or aren't addressed as directly as they might be. So NNs is for neural network. So one of the things about a neural network is that they function better when you give them some kind of random initial state, rather than either a 0 state, a 1 state, or a uniform state. And the question is why? And the answer I've basically arrived at is nobody really knows, but it's true. So I did do, leading up to this presentation, some self-experimentation in just like reproducing the significant results of other people. Partly started from, I'm like, well, I don't understand anything about all of this, so I'm going to build the simplest neural network I can, and I'm just going to ignore all of the things they say you should do that I don't understand, like cleaning your data and normalizing things or initializing anything. I'm just going to build a neural network and just like make it try and function. And then if that doesn't work, I'll like bring in what's like the minimum viable stupidest neural network I can make that works. So it turns out you don't need to do this just to get something that works, but you do definitely need to do it to get like reasonable results. I found data normalization was pretty much critical to getting something that worked. This was more like moving from kind of meh performance up to pretty decent performance. And I'm sure the answer is something to do with local minima and things along those lines. But one of the troubling things about neural networks is it's very hard to get like a really precise answer. It's more like, well, we've established that, you know, if you pull it out, the machine doesn't go as well. So there's a clear cause and effect relationship, but you know, they're just kind of too complicated for me to understand. So that's sort of the best answer I can give on that one. The next one was, what about a neural network models a biological system? It's a fairly crude approximation. You would perhaps describe it more as inspired by a biological system. So do you get better performance by just doing weird things that help with the performance of them that, you know, at the statistical level, or do you get better performance by improving the physical realism and fidelity of what you're trying to achieve? My guess is that it kind of depends on the goals. If you're trying to do like medical research, you probably want a high fidelity system, even if it doesn't give you as good image recognition or something like that. For image recognition and other generic purposes, I think a lot of people have stumbled into a lot of alleyways and find out largely by trial and error which ones work successfully. There's an active research community. I'm not a research grade thinker. You'll have to ask one of them if you want to get to, like, what are the underpinning, like, research findings associated with this particular trade-off. Certainly the neural networks that I'm using and that I've actually used, like, I've never tried to improve performance by downloading someone's more physically realistic model. I've only ever tried to do the kind of statistical tweaks that seem to generally improve performance. How do you explore a large data set? Large data sets are a moving feast in terms of how you define large, but I think there are kind of two definitions for big data that I quite like, which is like, one is like there's just too much data to reasonably understand, and the other one is it doesn't fit on a computer. They seem like reasonable starting points. So how to explore something that's just too big for me to understand? Like mostly visualization, sometimes domain knowledge. It seems to be hard to make a lot of progress in a machine learning problem without at least some basic domain knowledge and without a lot of graphs. Graphs and context and visualizations are pretty helpful. And then try to essentially subset your data visually into similar regions and try to understand some of the relationships in it. I think, so this second question came from the same place as the how do you explore person. And I think that person was trying to envisage, if you have a large data set, are there any kind of like relatively simple metrics you can get about that data set that are going to help you? And the answer is yes-ish. So there are things like, is your data normally distributed? Yes or no. If your data is normally distributed, then you can say, well, it's valid to perform various inferences because it's normally distributed, which might not be valid if it's not a normal distribution. So there are some things like that. You can work out, like, you know, what the median is and the average and the interquartile range or standard deviations around that data to get a sense of its kind of statistical variation. But that won't really necessarily tell you significance. I don't mean statistical significance, I mean kind of like real world significance. The computer's really not going to know how to understand the importance of what's happening, but you can definitely like characterize the statistics of the data that you're working with, and that's a pretty reasonable thing to do to start with. And one of the things you'll do if you have like weird data is you will need to effectively perform some kind of transformation on your data to make it more well-formed so that you get a good functioning out of your machine learning system. So it turns out that almost all of data science is that step. The like doing the modeling is like, it's like the 2% at the end. It's like, you know, I got a job, I have a contract, you know, hypothetical, you know, I got a new job, there's a contract that lasts a year. You could leave the modeling till like a month before the contract's up. Like that's how much work the data is relative to the modeling side of things. It's just less exciting and more manual. So we talk about the last mile a lot more, which is what we'll be doing today. Excellent. So does data preparation invalidate results? So I think the question's kind of like a couple of layers deep there. Like bad data preparation will definitely invalidate your results. Like you can definitely make mistakes while modifying your data and end up with invalid results. Unconsidered data preparation may produce a successful outcome but reduce the trust in what you're trying to do. So data normalization is an incredibly common thing. There are various other data processing steps you could apply. They will probably make your learning converge to a result more readily, but you might not properly understand what has happened in there, and when you try to apply it to other cases, you might find it doesn't work as well as you expect on new cases and new situations and new data, and you won't necessarily understand why, because you just shoved the data into the sausage machine and ran the things and it seemed to work okay on your machine, but the risk of it not generalizing is pretty high. So installers in the room, how are we going? Is the network up?
Do you actually need the whole Anaconda installer stuff?
No, if you have Miniconda, that should be all right.
It's like 300 megs or something. I did Miniconda. Okay. Awesome. Thanks.
That's the Arno sources included. Is it like a sub-module or something?
No, I'm getting it from, I can't remember. I think I'm getting it from doing a pip install on that one.
So in your install.py, it tries to do a pip -e install on the source package of Theano.
Yes.
When I clone git repo, that directory is empty.
Okay.
Submodule from another.
No. There is a GitHub module. I thought I referenced the actual GitHub URL, but.
A funny icon in the GitHub page, but it's not clickable.
Okay, so the workaround is just go clone Theano and just pip install it manually at the end. There was a thing where like the current release version of Theano is broken against the current release version of some other thing, and the solution is to get their current, or
No particular commit, just
yeah, no particular. Well, I mean, look, I must have some particular commit out on my local machine, but fingers crossed, it will just still work on the head. If it doesn't, yeah, all right. How about I go look up where I'm actually at? And then you can do a git clone, try install it, and if it doesn't work, I can look up where I'm actually at. Where will it have put it? Yeah, one of these days I'd really like to there should be just like some kind of git name key value pair in the sky that I can like assign random things names to so that we can share them. But in the meantime, there's the commit ID that I based my tutorial on anyway, but I expect the current head will work. All right, who else is somewhere? Yeah, sure, that probably works fine. I can't remember why I went with Anaconda instead of pip. At some moments in time, I was finding things hard to do with pip on OS X. It's like the underlying technology is like reasonable, but a lot of it's essentially coming out of academia, so they don't really necessarily have all of the testing procedures in place to make sure the stuff's valid all the time. So I found Anaconda generally the best virtual environment manager for my Mac.
I also install Python 3.4.
Yeah.
Maybe Conda fixes this, but on Python 3.4, the latest version, Python-notebook isn't a package. You want to install Jupyter, and that installs notebook.
Interesting.
Conda install, it doesn't work with pip, so I just...
Yeah, okay, cool. That makes sense. All right, well look, rather than hold it up a whole lot longer, what I might do is just keep trucking, and I'll stop in every now and again and see how. And I'll tell you what, the first person who gets an install done, stick up your hand and we'll do a round of applause. Okay, still broken, fix it yourself. Okay, so look, recent news. So machine learning, data science, it's like moving at breakneck speed. Like, I didn't even get round to including some of the things that happened in like the last week. I like can't keep up with the news, it just goes too fast. So one of the big things is Google released a thing called TensorFlow, which is like, you'd think of it as like the low-level API or mid-level API to doing machine learning using your graphics card or CPU. I've got a thing called Theano, which is kind of like TensorFlow. So you can, and the thing I'm using something over the top of it because it's easier, and the thing over the top of it is called Keras, and that can back into TensorFlow. So, you know, these things are sort of pretty chop and change. So if you sort of think, well, hey, TensorFlow is amazing, everyone's using it, well, there's actually a nice, easier kind of way of stringing your neural networks together over the top of it, which I really like. Although it's by a whole bunch of research people, so the API changes every 6 months and the order of the arguments flips and you have to retest all of your code. But it works well. In December 2016, some fairly famous US people brought into life a non-profit research institute for OpenAI, I think they're trying to solve the don't be evil AI problem, but it's a little unclear because even though they say it's all going to be open source, it's still, they don't actually have anything out yet because it's all very new. January 2016, Google, who also released TensorFlow, released a Udacity course on using TensorFlow. So I generally try to steer clear of strong branded recommendations for things, but I mean, it does give you that coursework, so that's quite good. And also this year in January, Baidu released, the Chinese search giant with Andrew Ng in it, released this thing called Fast CTC, which is like amazeballs speech recognition. I have never attempted to use it, but I'm told that it is the quickest and the best at the moment. So things are moving incredibly fast. So it's very hard to know what to do. It does mean that you can do more and more on your desk though. So even though the world is moving very fast, it is also commoditizing a lot of this technology. And a lot of bold claims get made about AI/data science/machine learning/ a very large number of synonyms. So some people are worried about the AI apocalypse. If you went to Paul Fenwick's talk, he alluded to the AI apocalypse, essentially where it's a technology that may, in some sense of the word, get out of control or be miscontrolled or misdirected or in some way dangerous in ways that we don't expect. And some people are very, very concerned about that to the point where they're making very dramatic claims about its threat to society. Other people who actually work in the area say, look, no, we're really, really a long, long way from that being a particular concern. We're just kind of happy if it runs at all. And then there's the general experience of data, which is like mostly spreadsheets. So I think most people will come into data through some kind of data set that they're given at work. It probably won't be huge. It may, like some people will have very large data sets, but like most, like sort of individual humans, when they first come to data set science, will either be like, gee, there's a lot of really interesting stuff on the net, I'm super curious, or their boss will go, here's a whole bunch of log files, tell me what's important. Okay, so why is it suddenly a hot topic? So I see that we have an emerging, I don't know if you can call something that's converging also emerging. I should probably have considered this a little more carefully. The juxtaposition only just struck me, but there is nonetheless an emerging convergence of paradigms, which is effectively the data representation and the algorithms on which machine learning and data science are based now much more interoperable between different kinds of data and different sources of data. So we're moving to more vector and matrix-based data, which can exploit array-based processing, which is better for GPUs. We've got these networks of these arrays for the information processing model. There's a convergence between algorithms that will comfortably work with, regardless of whether you have images or text or statistical information. Physical modeling is still its own thing off on the side, so like weather models or simulations and things like that. Like so, if one path represents like an adherence to a strict physical realism, the universe can be explained, it behaves according to predictable rules, and we should put our effort into understanding those rules, a very kind of analytic view of how to approach problems, versus a more statistical, black boxes are getting really, really powerful. We just need to learn how to use magic boxes better than we did in the past, and magic boxes will help us take great strides forward. And at some point, they'll be so magical that we don't even need to think about whether we can understand them because they'll understand themselves, and so on. So, look, that's all very wonderful. Let's talk about what we're going to look at today. We're going to look at something called the random forest. This is like the Swiss Army. Well, it's only a single option. It's like, so I can't really call it a Swiss Army knife. It's just like the knife. I don't know. I'm lost here. My analogy's gone. It is the best, most commonly applicable, ubiquitous tool you can get a pretty good solution to basically anything with. It is remarkable at the degree to which you can just throw data you don't understand into an algorithm you don't have to think about and get output that is like pretty useful, really. So it is the fundamental starting point for anything. Then we've got a few other techniques. There's something called gradient boosting, convolutional networks, which are particularly focused on image processing, which exploit by their nature some of the inherent 2D structure in an image by mimicking that structure in the network itself. Vector-based concept representation and deep learning, which deep learning just kind of means big neural networks. Okay, so limitations and bumps. Practical issues and data munging is a huge issue. Handling poor data, dealing with irregularities in your data, enormous troubles there. but we're just going to kind of wash over them because they're very large and require a lot of manual consideration. So we have not automated thinking about data yet. We've automated like drawing inferences from a good representative set of information, but that turns out to really be very hard deciding whether it's representative. And so far, there's not just like a kind of, is my data representative tool that you can run over your data and have a lot of confidence about it. It would be quite useful, and I'm sure there are some techniques, but you need an appropriate amount of expertise in them. So physical modeling and identifying causation in your machine learning, that's a tricky thing. Hypothesis testing is a tricky thing. Induction and deduction beyond correlation. Correlation is not causation. Your machine learning cannot tell the difference. So it's very easy to look at some of these things and go, that's very powerful, which it is if you use it properly, but then you can find that it surprisingly has a lot of shortcomings in other regards. Things just inexplicably won't work just all the time. You won't have a clue. You'll just have to try something else, and that something else will work, and then you just kind of move on. There are probably people at the research grade who would be able to like understand the causal, the real, exactly what's going on there. But things like, how big should my network be? How many inputs should I have? What kind of activation function should I use? How should I, all of those, they don't just have just specific answers where you can understand how to use one or the other. As far as I can tell, people either just automatically search through all possible configurations, or they just human trial and error is one of the really common things. So, and then later on, there's these things called adversarial examples where the computer falls over and it really challenges your belief in whether these things are actually generalizing from the information or whether they're just really good at remembering things. Okay, so here's our tech grab bag. Python 3, you're not going to make silly integer division mistakes, which you definitely don't want. So Python 3 is a better choice than Python 2 for these applications. A list of packages, a list of algorithms we've mentioned, and I'll talk about data pre-processing as well, because that's one of the fairly powerful techniques. I'm coming up to our first worked example. Maybe I'll pause. Has anyone... Excellent. One person, all right. Oh no, a couple up the back. More claps. Okay, so I'm more than happy to pause for 5 minutes, do some tech support. Does anyone want some tech support? Yeah, all right. I'm going to turn off the microphone so that I can give tech support without any concern for what might go over the radio and get recorded. All right, everyone. In the interest of time, I think I'm just going to have to go with moving on here just to keep getting through the available time. But I'm more than happy to stay afterwards or help people afterwards on other days as well. So I'm just going to go through moving through some of these things. And thanks to everyone who's helped other people get up and running as well. In many ways, just getting people have everything installed is probably the most useful thing I'm going to do today, because everything else, the slides are in the repository you just cloned, and everything can be worked through. So how I started approaching this was the reproduction of significant results. I thought that was one of the most interesting ways to get to grips. It's hard for me to know, like there's going to be a diverse range of previous experience with these concepts in the audience. So the first example, at any rate, will be one that people who've encountered this before will almost have certainly worked through as a very early example. But on the other hand, it's actually a really impressive result for machine learning. It's a fairly old problem example, and it's basically how postcode-based digit recognition works, and pretty much how all handwriting recognition works. So session 1, images. So the neural network's input will be a single slice of this image, but the fundamental technique doesn't care how big your image is. It doesn't care what resolution it's at very much. You'll need to make it grayscale. Most image processing just works better in grayscale than it does with colors. You can do things with colors, but a lot of the time, many problems are just going to be better solved by going to grayscale anyway. So what we're trying to do is work out, well, how do we recognize these digits? The first thing we're going to look at is something called a decision tree, and then we'll go up from that for a random forest, which is the technique we'll actually use, and then talk about some of the other techniques. So who's seen a decision tree before? Has anyone manually written a decision tree? One up the back there, one at the front. So a decision tree is not a bad way to represent something that's fairly rule-based, fairly threshold-based, where there's like a clear policy. You could well imagine like a warning or something where you need to send a specific piece of information at a previously agreed threshold or a previously agreed likelihood. And this represents this example, like, do I go and play outside or do I not go and play outside? I've got 9 prior examples where I went and played outside, 5 prior examples where I didn't play outside. And this tree effectively represents what was going on in those situations and what kind of decision making, segments that input space into a decision to play or don't play that works for me. Now, one of the things in this example, it's like 3 zip, zip 2, zip 3, 2 zip. So it's a very clean segmentation. There's nothing inherent in what's going on here that means that this couldn't be 3-1. For example, you may find a decision tree doesn't fully resolve the decision at hand, but still gives you a really good indication. Like, 3-1 is still a pretty strong preponderance of going out to play, for example. So you might be able to find thresholds that allow you to fully segment your space, and then whenever you come up with a new example, you'll get you should definitely do that thing, or definitely not. It is also possible to utilize these things to give you a likelihood piece of information. If you have a larger state space, you're more likely to be looking at a likelihood situation. And one of the tuning parameters is how many layers do you have. So here we've got just like sunny, overcast, and rain, but you might have, for example, like raining a little bit, raining medium, raining a lot, etc., etc. And the more resolution you introduce into the degrees of raining, the more you're going to be able to have independent categories coming out of the bottom of your decision tree. So this is quite a good sort of human understandable representation. But what a random forest is a collection of somewhere between, really typical numbers would be somewhere between 10 and 1,000 of these taken as a collection and used in a way that you average the results from all of them to achieve the desired result. So that's what the random forest is. So I'm going to pull up the prior examples. So there we go. So we're going to be looking at this MNIST. MNIST is the name of that group that produced that data set. So MNIST here refers to the data set and the problem example. And we're going to start off with a random forest with 100 estimators. Now, 100 estimators, so I've basically just nicked this from an online tutorial and just adapted it to make sure it worked in this context. So because MNIST is such a common example, many of my examples load the data differently because I took them from different places. So I wouldn't really worry about it too much because it's all parameterized. But let's take a look here. So loading the data takes a few seconds. This is just modifying the data into a couple of different examples. So X here is like the input cases and Y represents the desired output for those cases. So most machine learning is predicated on, I don't know, kind of like, it's very, I'm making it up, but like 60%. Like really, like there are examples where it's unsupervised, where you're more discovering inherent structure and your goals are like less well defined. But a very large amount of machine learning is actually, I've gone to the trouble of creating really clear input-output cases from past data, and all I really want to do is really effectively match future input cases against what's going to happen in future. And that's what's happening here. So X is the prior examples, and Y is the desired target state. So in this case, the numeral that we're trying to implement. This is it here. These 4 lines do it. So, it's gone down to a 1-line function call. The number of jobs, I think by default might be 1, and I think the number of estimators by default may be 10. So I've tweaked the default numbers just slightly. So this will go and take a minute and a half. So I'll look ahead because I ran this previously and thought, oh, well, I don't want to stop for a minute and a half every time I want to do something. So now what we're doing is we've got this extra data set called test data. So this contains examples that the computer hasn't seen before. So one of the things that's just really common is if you go, well, why wouldn't I just train on all of the information I have? And the answer is that you will find that if you do that, your guarantees around being able to predict things in future are not going to be very strong. This thing here is essentially telling you your confidence of, well, how well does the past map to the future? So we've created a bunch of cases. They generically represent the past, and this bunch of test data, which in some sense of the word represents hypothetical potential future cases. So we've segregated some, again, representative part of the data, which is another source of issues. If you don't have representative test data, you also can't trust whether the test data is going to be relevant. Nonetheless, in this case, you randomly select it, hope for the best, and move on. So we do the same kind of data preparation. In this case, the prediction is much, much faster. So, somewhere between 3 and 5 seconds, depending. And, on appropriate machines, this is effectively an instant operation. This is a web time response. It might not be instant, but it is more than sufficient to be including live on a web page, for example, like that. So how did we do? So we had 1,000 examples and we got 9,002 of them correct, 998 of them incorrect, and I can do this in my head, but nonetheless, that represents approximately 90% accuracy. So, that's pretty solid. For very little effort, for no real prior knowledge that this was going to work or what I needed to do the data. I might have experimented a little bit with a number of estimators along the way just to go, what's going to give me the optimal result? But if you were, for example, faced with a problem and you wanted to go, well, how far can I get in an afternoon? Well, what you'd find is from midday until 4:45, you could spend preparing your data. From 4:45 to 4:55, you could run this, validate the outputs, and email your boss, and go home 5 minutes early, and you're very likely to get a good result. So that's what you would use random forest for. Now, some things, 90% is quite an acceptable error rate, but the question naturally arises of how far we can push this approach with the random forests versus the effectiveness of other solutions as well. So what we have here is 1,000 estimators. So I've just increased the main scaling factor on the algorithm by a factor of 10. And we go through the same thing. The training in this case takes a lot longer. So using 1,000 decision trees to try to model the space takes nearly 8 minutes. And the actual execution time increases up to 14, 15 seconds. So that's probably still fast enough for a page load, depending on how heavily loaded your server is and how patient your users are and what the value is. But what we really are interested in is what did that buy us? And in this case, it bought us very, very little. It bought us the difference between 90 and an infinitesimal and to 90.5%, roughly. So it's a very, very small gain for that amount of time. So you would probably come to the conclusion that the main issue here is the fundamental capability of the algorithm at hand rather than the parameterization scheme you've chosen. So that then takes us into, well, okay, how can we go further? Well, there's more than one way. One of the other sort of main topics is this neural network approach. I'm not going to go to the trouble of explaining the details of how a neural network functions, except well and mysteriously and not as fast. And one of the main reasons not to explain it is that the fundamental explanation of how it works actually doesn't tell you how well it works. It's just an inappropriate way to explain what results you're going to get. I can talk to you and explain what these things are doing and how changing some of these things might affect your network, but an underlying mathematical explanation is no more useful to solving a problem than a basic explanation of how a brain works or how many things work. So the the use of it is quite different to the understanding of it. So let's go back to our examples here. So what we've got here is a neural network. We've got a few neural networks. One is a convolution network. This is I'll just call it flat network, flat network structure. So again, we've got some data that we load, and we reshape our data exactly the same way. So this is where we start using this Keras library, which is kind of my favorite one. We are going to do data normalization. So back when I said what's important and what's not important, this is important enough that if you don't do it, you're really not going to get the same kind of performance at all. So yep, definitely do that one. Keras is configured up to use the Theano backend. We go down now. The initial example I tried had multiple layers. So I went through the exercise of how much can you remove before performance degrades. And the answer was, well, basically all of it. So we've got a few things going on here. I've got this layer 1 size. I had this theory that I would create multiple similar layers by using this as a parameterization, but only really needed one layer. Also, from a mathematical perspective, as I've read but don't understand, in theory, a large enough single flat network will give you pretty much the same predictive power as a less large multi-layer network. Hand at the back, someone who knows the answer properly. So I think in terms of the speed of Sure, so the question was, is there a performance trade-off between short and wide versus deep and medium? Like there is a certain minimum whereby if you make your layer like much thinner than the number of genuine classes of thing you've got in your data, that you just lose that information. So you do need a kind of certain amount of ability to distinguish between the various input factors. It will take probably, and this is just based on personal small experience just for the self-learning. This isn't like representing truth or anything like that, but my experience has been that flatter layers tend to be a bit more predictable in terms of whether you're going to be able to get a result in terms of training them, and deeper take longer to converge for me. Yep.
I think you get a lot of overfit if you have too many layers in
Yeah.
circumstances.
Yeah, you'll get overfit whether even on a flat one if you just have too many nodes. So probably too many layers, but definitely too many nodes overall. Yep.
So just going to the theory, as far as I understand, as you go deeper into nets, you're actually doing generalizability, and when you do flat layers, you're actually talking about specificity. So if you want to know whether a polar bear is a polar bear based on a very specific image of it facing you, then you'll have a flat net curve. You want to do, okay, but even if it turns away from me, then you'd be looking at more layers, because more layers gives you more generalizability, I believe, if you want to think about it in that way. And that goes back to power as well.
So my understanding is that's theoretically true, but only in a kind of mysterious post hoc rationalization sense of the word, rather than a kind of theoretical explanation of what the layers are for. Like, in theory, you could imagine, say, training one layer to do, like, look at one aspect and another one that does another aspect. And so I can totally see how, like, one layer could recognize, like, generalized image structure, and another layer could recognize, like, panda bears out of generalized image structure, and you might even be able to reuse, like, layer 1 for multiple, like, there's room for generalizability there, but, like, for convolution, and you see that a bit with convolutional networks, but a lot of the time, saying that that's really truly what's happening deep down in the mud, I think is actually a longer stretch. Yep.
Just to add to the last point, I think the more layers you have is kind of related to the order of the problem. So if you plug math problems into it, the higher the order, the more layers you need.
Okay. All right. So happily moving forward out of territory I don't know much about. Well, let's have a look at the performance of this particular model. So this is basically the flat model. So what we have here is a dense layer, which means connect all of the top level into your input nodes. This thing here is called a linear rectifier, which is mainly like it's like the abs operation. Basically, it just makes everything positive. This thing here is a thing called a batch normalizer. If we had a large enough data set, one of the things you would do is, rather than training the network on all of the data at every iteration, because there's an iterative approach, you would just train it on like randomly selected subsets at a time, just to make the whole thing more tractable. And this says just magically normalize that information as it comes in. So this is an interesting one. This says just with a random probability, just ignore 50% of your input at any particular point. So just ignore 50% of the pixels in the image and just try to do your best in that context. So this is another one of those techniques to avoid too much focusing on very specific details. It's supposed to be more general as a result, and in general, you are more likely to train faster with doing this than not. Then what we have here is now we're changing the shape. So we've connected all of our input nodes based on the dimensionality of the input data up to the size of our intermediate layer. Then we're closing off back from 1024 down to the number of classes. And there's a number of digits, so 10 of those. Then we have this final activation function. Okay, so here we can see some relatively pretty output for how it's going, which is quite nice. And so you see it's got the number of training iterations. You get some information along the way about how it's going on that data set. So it's able to, now I can't remember the loss function on this thing here. And to be honest, I just move on and do my own calculations later, because the loss function might be like a squared error thing, and the behavior of the training varies with the loss function you choose. So I just don't really worry too much about the exact semantics of what loss means in this printout. I'm just like, okay, good, it's just going down. So the loss is going down over time, and then I'm going to use the statistics that I can just kind of much more easily understand. Okay, so now we take our test data, and we do all the same kind of stuff, and we zip it up, and we go, we've got 10,000 input cases, and we go, well, how many did we get correct? Okay, so this time round, last time you might remember we got 9,000 correct, now we've got 9,700 correct, 764 and 236 wrong, and we've cranked our way to not that far off 98% accuracy. So I still haven't thought very hard about what I'm trying to do, but I guess I've made a few decisions. I've picked a network shape. There's no one obvious network shape to choose. You probably want something with like quite a lot more nodes in the middle than you have your input, size of your input. Yes, question there?
Can you get it to report confidences rather than prediction, like actual predictions?
Yes, so I guess there's a few ways of doing that. So you might, for example, want some kind of error bound around your prediction and some kind of context for on the data, like, how bad were the wrong ones wrong? Even though we've got 98% accuracy, could that be even higher if we accepted some tolerance, things like that? So I think most of that would come from taking there's one thing called k-fold validation, which is where you take your data set and divide it up differently multiple times and walk through it in different ways, and that can do it. Or the other one is if you have enough test data to run it on a lot of different test examples, then you could start to just derive that in a black box sense of the word and just go and then develop some of those characteristics around like mean and variance and things like those. I don't think there's just a kind of like magical one-liner API call for what you're talking about, but it would definitely, if you're going to use this in like a production system, you would definitely want to be able to talk about, well, how wrong is the worst case? How wrong is the average case? That kind of thing. And there's just not quite enough space for a proper exposition of that here. So I haven't really prepared down that path a lot, but it's a very good way to take it to the next step. Okay, so then what we're going to go to is what you would consider to be the gold standard for image processing for ordinary image processing, which is this thing called a convolution network. A convolution network essentially is a two-dimensional neural network. So the one we had in the past lined up all of the pixels just like it didn't care where any of them were. And like they would have been effectively in the array order if you had flattened the array. But if you had randomly sorted your image and you did that consistently, then the algorithm wouldn't care. Like it just pays no attention to the relationship between where pixels are relative to each other. It just starts to learn about the significance of like pixel 1 and pixel 2 and pixel 3 and pixel 4 and remembers on that basis. And it's kind of surprising it works, but there you go. So the convolutional network goes, okay, now what I'm going to do is have shape to the actual network. So this bit here, this is the nature of that layer here, and this is where we're using the X and Y extent of the image to determine the shape of our layer. So we have stepped from something where the network design has no semantic relationship to the input to one where we do have a semantic relationship in the network design to the input. So in some sense of the word, you might sort of breathe a sense of relief and go, oh, thank goodness something in here bears some kind of meaningful relationship to the problem I'm trying to solve. I feel better about that. But I wouldn't believe in it too hard. Okay, so what we do here is we build up this network and we do our training, and this time it takes a lot longer. So it took this machine more than 3 hours to do the training. So from the 90% accuracy in 5 seconds up to the 98% accuracy in 20 minutes up to, we'll see in a minute, in 3 hours, more or less. So there we go. So here it's doing a very, very slow amount of training. 12 iterations, still not a lot. You know, like many problems, you might do 1,000 iterations. That might be worse than 12 iterations. You won't know in advance. It's pretty freaky that way. But you know, many people will go to that much trouble and try it out. So this model is also deeper. You know, it's got the convolution layer and this thing called a max pooling layer, which is about effectively like downing the resolution of the thing coming from the previous layer. We're dropping things out, we're flattening them, we've got 2 activation layers. You know, it's all going on here. This one, where's my previous printout from the one I did earlier? All right, you may have to just trust me that the answer for how accurate this one is approximately 98.2%. So it is better than the other one by a bit less than a full percent. So it's a lot of effort to get a small amount of benefit, but sometimes that benefit is worth it. You might think, well, hang on, 1% is a pretty small increment. How do I know whether that's a reliable benefit I can expect to see in future going forward, or whether that's just a kind of interesting feature, but not something I should really rely on? Can I really say, hey, I've really taken a step forward here, that was a pretty important nearly 1%, or is that actually a pretty irrelevant 1%? And I don't quite know how to, I haven't really prepared a response to that here. Again, like along the lines of your question, that kind of investigation of the reliability of your results I haven't stepped into as much. Yep?
In terms of like the example before, like being 90% right, if that's like, it thinks 8s are always 9s and it just doesn't know anything about it. How do you try and explore that and work out whether it is something like fatal instead of something a bit iffy?
Sure. It's a very good question. I can make up the answers, and some of the answers will be, essentially it's going to be data exploration. So like one of the things will be like checking the distribution of your predictions. So one would be like, does the distribution of your predictions match the general distribution of the input cases, for example? So you could take all of your predicted outputs and check that you have an equal number of all of the different output conditions. Or if you have normally varying data like how tall are people, and then you have this predictor based on, say, how old they are, is the statistical prediction of your distribution of your output the same as your input, if that makes sense? So if I'm going to predict predict heights at 30 on the basis of the height at age 15, for example, and I have and I have all of my data and I do all of my predictions, do I get a realistic, real-world distribution of output values or not? So like another example of that is like predicting the average can sometimes perform well statistically because it's like an unbiased thing. So you might go, oh, I'll just predict the average for everything. Hey, I'm fantastic according to this one measurement of am I biased or not? And that's where you need to probably go to a greater, like what do you need of your data? Maybe you only need unbiased data, and it turns out you didn't need to do any machine learning at all. All you needed to do is work out the average height of a human and sell t-shirts on that basis. Or you might go, well, how many t-shirts do I need to order of each size? In which case you want to make sure that your output distribution is reasonable. Yeah, one more at the back there.
Yeah, just an observation on the last two questions. When you think about it, the last output of your layer is the guess, right? So if you focus on one, say just focus on the number 4 and then go back into your function and change the threshold level, you can do two things. First, you can change the threshold to see how confident it is. And the second thing, you can actually look at one number and change your function to see if it's performing the way you expect it to perform in isolation. Just by looking at each the last layer network is the output.
So I've got a few things that I've used to look at, like how do you know something is right, and I've taken more of the how do I benchmark it rather than the how do I check it's realistic sort of bent. So one is it worked on my machine and I just got 98 coming out of my thing. That's one starting point. The other one is like if you're a domain expert, does that seem plausible? Are you radically far away from other known solutions to the problem in terms of your performance? Benchmark against some other kind of predicting system like weather forecasting, like am I at least as good as a weather forecast or not as good as a weather forecast, for example. So benchmark yourself against other people with different but similar problems. You can say, I'm as good as some other technique within Y% likelihood of the time. So the example there might be the random forest might be your benchmark. I'm as good as a random forest 78, 90% of the time or 100% of the time or whatever it is. Or I'm as good as a human expert X% of the time. So just start to draw context into your performance. And the other one is account for a percentage of the error. So for example, you might benchmark against an average predictor. So you just go, I'm just going to predict the average every single time. Well, how much better do I do than that kind of standard? So a lot of it's about finding ways to relate your performance to the performance of other alternatives. So this is one of my favorite ones. It's called the R² or R2 test. And it's essentially this is the average predictor. So you can effectively use the same mathematical technique. It doesn't have to be the average of the data set. This one assumes you don't have a known benchmark or competitor alternative, but you can use the same approach where instead of having a horizontal line, you have whatever the predictions coming out of some other system are, and then you go, well, at every single data point, there's my prediction, there's the competing alternative prediction, and that you can break the error into these components and talk about the ratio of those things and effectively do a sum over the examples of those things, and that will tell you how much of the variance in this data is your model explaining through its performance. So that's some of these, this might be more appropriate for like a researcher or a data scientist than for a general audience person. So if you're trying to explain it to the public, I don't know that I would necessarily take this approach, but if you want to evaluate it for yourself, particularly if you have some genuine alternative, that can be quite useful as well. So if you were going to compare two different models, one thing to do would be to compare them both as their, what is their R2 score and which one has the better R2 score. The other one would be more like an intercomparison where you replace the average line with the other model and it's say relative to the other one, how much of the variance am I explaining? But that is but the tip of the iceberg. The other one here is, and this goes back into your example about well, what if I just don't know anything about the number 8, but I'm otherwise doing well? What is the nature of my error? So this one is something called the relative operating characteristic and the area under the curve. And effectively, suppose I've got a true-false situation, like heads or tails. I'll just go heads, 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 heads. I'm going to get 50%. Now, if I just go, well, the height of a person, and I just go 5'8", 5'8", 5'8", 5'8", 5", all of the time, well, sometimes that's going to be true. In fact, I'm going to get correctly 100% of the time when someone's 5'8". So I get really amazing correct recognition of people who are that tall, but I'm going to have ridiculous false positives. So this graph effectively expresses a relationship of your algorithm at different levels of certainty and rate. And this represents effectively the 50-50 line, and the more towards this direction your algorithm is capable of achieving, the better you've got. And effectively, the algorithms will often take a tolerance in there somewhere, which is why it's not just a single digit. Yep.
In the case of highly skewed distributions like anomaly detection or payment fraud detection, how well does the ROC or AUC perform, given that we have to take into account true positives, true negatives, false positives, false negatives, and how does it compare to the another measures, say, such as the F-score or F1? I don't know what's exactly the correct notation.
Sure. So you will not be able to rely on a single measure of performance in general. There's no single measure which tells you all of the things that you need to know. This tells you a reasonable amount about your performance, but it doesn't tell you everything. So what I would suggest is that you develop a model of the kind of error you want to avoid, and then measure it against a score that's going to tell you something about that negative consequence that you're concerned about. So for example, are you best off to be just kind of like unbiased in terms of your accuracy, or do you actually more concerned about, I don't really care how accurate I am, I just don't ever want to drive off a cliff by accident? It really depends, whether the worst case outcome is the problem or the average case outcome. And there'd be literally 30 different measurements you could do which take account, which will give different importance to different aspects of performance. All right, so session 2, I'm going to barrel on. So I think I've got you all till 5:20. So we've had the pleasure of going a little slower through some of the first examples. So I might have to go a bit quicker through some of the second example to compensate, and still allow some time for some tasty treats at the end kind of stuff as well. Okay, so what we're going to do here is something called word-to-vec. So this is one way to get into looking at how to represent text data, so a fundamentally different kind of information. So I'll talk a bit about the data representation and then effectively race through the fun example, and then people can work through it more at the end. So word-to-vec uses a neural network training approach to word recognition, where effectively every word gets its own number. So it will be like 00000 drink bottle bit 00000 would be the representation for the text drink bottle. I mean, that's a 2-word example, but we bring them into, you would regard that as a single concept in the processing, and then phone would be like 0000 for the drink bottle bit, 0001 for the phone bit, etc., etc. And then so you actually have a pretty wide input representation there, because you literally have you have as many nodes as you have words in your lexicon, say the English language, and every single one of them is going to have a 1 in the appropriate location. And this approaches the problem by saying, well, the weightings for how you then do your the layer above that, the layer that's actually doing the weightings, captures to some degree how much phone concept is there in the drink bottle, for example. So what you want to do is predict, given a few previous words, what is the next word likely to be? And that gives you some sense of association between pairs of words or triples of words or quads of words, things along those lines. So it works best when, at least at the training stage, you have a very large set of data. So you might choose like all of Wikipedia or five or six Gutenberg books or something along those lines. So you might need quite a lot there to capture your input state. But then you're on your way. So you have these things called n-grams, the sequences of words, and you try to predict the last word of the sequence based on the same kind of technology. So this example's in the MNIST. It is not in the MNIST directory. It is in the word2vec directory. Apologies. And yeah, I've got a silly demo. I'm not going to run it live because it involves scraping Twitter, making random associations, and sticking them over the top of a random image. And while I've got safe search turned on for all of those, there's no good taste flag. And so I'm not going to present anything in poor taste. It will normally be okay, but I'm not happy with normally okay for a live presentation that's being recorded. So I think, well, look, all I'm doing is giving you the ability to reproduce the process and show you some prior results. The intention is not to produce like wildly controversial material. It's just that like angry people use Twitter, and sometimes that ends up being the input data. And you know, like, laugh now, cry if you don't do this, cry when you make a web page based on some of these techniques and you didn't take account of it. You know, you can get in a lot of hot water doing this in a live environment because it's very sensitive. People's reputation and a company's reputations are really important things. So it's really interesting to be able to explore the technologies. You can get a long way quickly, but you actually really need to take account of these factors and take them very seriously if you're either going to be talking to other people about them or saying, go away and do this in any kind of live environment. So what I will do here is walk through, I'm going to actually pull up my blog post on the topic. So what I've done in the memebot is that I've looked at taking words out of a previous tweet. So I'll pull up the code as well, because there's nothing problematic about the code. It's really just input data sensitive is really the main issue. So here we go. Okay, so we have a collection of things here, including this word2vec library. My real Twitter credentials are not in the source code, so you will find that you need to add your own Twitter API keys to make this work. There's this lexicon called text8, which represents the source input for the text. And this is my Twitter connector. So I go and get the public tweets that other people have made off my home timeline. This one here chooses a number of words, finds tweets that are long enough with enough real-world words in them. So I avoid things like and but, because they tend to produce highly abstract and not very interesting results. Go through here, check that they're words that actually have appeared previously in my vocabulary, because it's not really possible to act on previously unseen inputs. And this is where what we have here is we pull out a number of the words out of that tweet, and what word2vec will allow you to do is make an analogy. So you could take any two random words like tall and table and find the same relationship between, for example, you could say, well, what is the appropriate word for a light globe? And say, well, okay, maybe it's going to be a small light globe, for example. I mean, it will be able to effectively navigate the semantic relationship between tall and table and apply it to an entirely new context. So this is where what I've done is grabbed a tweet from John Dalton, who's, I think, up the back there. Hey, John. So this is something he said, so I can blame any bad behavior on his public tweeting standards. So, of course, so he's tweeted something, you know, obviously after watching one of the presentations. So the words we're going to look here to have associations with is the difference between still, exceptions, and have, no, longer, in course. So they're the kind of, they're the words that we're considering. And this is the thing that came up. So still is to exceptions as have is to no longer. So It's not entirely meaningless. It sort of I don't know why it's picked the picture of spoons. That's pretty perplexing. So this is where like there's something going on. Like if I pull up the Twitter meme bubble, like awesome is to test, you know, like functional, I guess, as still is to spacecraft, like stationary is to, I'm like, yeah, I agree. That, like absolutely. If you've given me some untested code, like just look at the presentation, that install script almost worked. Okay, so almost is to test as still is to spacecraft, jammed over the top of a Flickr top search result for one of the other words coming out of the tweet. So, like, but obviously it doesn't make enough sense. I think people would probably go, well, hang on. If he's claiming this is the AI revolution, he's wrong. So part of it is because I need to do more work. I would have liked to have done it for this presentation, but instead I was adapting to the fact that my previous Flickr REST search API was broken and I needed to write a new Flickr image searcher. So my 3 hours worth of improvement of this algorithm turned into 3 hours of code maintenance. So let that be a lesson to anyone changing APIs. So a few of the differences here is that some of these are very generic words. So it's not doing any relevance testing when it's choosing its initial words. So it would be quite easy, for example, to do a more intelligent selection of the original words and perhaps words that actually do have a stronger associative meaning as well. So in this, I'm just taking 2 words and going, just give me the abstract conceptual relationship between these 2 words, almost and test. Take another one, which is still, and just give me the similar relationship with the word still. But these are very common use terms. The strength of that relationship may not be very strong. Word2Vec will tell you how strong that relationship is, as well as what the analogy is. So an improvement to this could be, for example, choosing words which do have a strong relationship in them rather than ones that don't as well. But it definitely gives you all of the basic tools to go through. So this one's kind of fun. Trivial is to break. It's a good start, right? That's a good start. Question and switch, not funny. I'm lost. But I don't mind the Trivial Pursuit background. I thought that's kind of captures the sort of the chaos of a broken system somehow for me. So I don't mind the associations. It's a good bit of fun. But if you want to do some kind of professional version of this to actually deliver outputs, this is why it's harder than an afternoon's worth of mucking around with the libraries. This is where you start to extend into you really need to start thinking about it and why there's still so much human evaluation in the loop for these things. All right, so let me run back to the slideshow. Okay. Oh, that's interesting. Okay, so yeah, the rest of it's really me talking about just some general techniques. So my computer's hidden the time for me. How am I tracking here? 20 minutes. Okay, that's good. So yeah, again, just feel free to interrupt. I'm very happy. I'm actually really glad everyone has just been interrupting with questions. I think conversations are more interesting than blurgs. There's plenty of blurgs on the internet already that people can watch, read, understand, and consume. So let's continue to do that. So what I'm going to go through here is an example of a few visual mechanisms for evaluating data. So the first one, these are kind of, I guess, they're kind of my favorite and maybe a little underused. So heat maps are a really good way for expressing some kind of two-dimensional relationship that isn't spatial. If you have a spatial relationship, obviously put it on a map. But this is basically the same thing. It's just like, you know, time of day. So you can just instantly see effectively peak times, variance, intensity. You tend not to, the advantage of the heat map, I've deliberately not put a scale as to what the coloration means. So you can significantly impact how someone's going to interpret something with the way you put the visualization up. Color is a terrible way of expressing a specific number because, first of all, eyeballs are often very different and none of them are that great at resolving like a decimal fractional difference in some kind of scale like this. But they're good for making people not get focused on the details you don't want them to care about. So this chart doesn't really tell you how many pedestrians there were, but it tells you quite a lot about whether one day is a lot like another day and whether 1 week is much like another week or not. So that's one of my fun go-to plots that I don't see quite enough of. There's still some problems. So most of the problems are the future may not be like the past. So we've had a bit of a conversation about this before. Sometimes those ways are predictable. So for example, it's quite predictable that winter will not be a lot like summer. It is even reasonably predictable that El Nino years will not be like other years. And it's probably predictable that things like population will continue to increase and taxes will go up and we'll all get older. So there are some things where it's predictable and there are some ways in which it's entirely unpredictable. Within the unpredictability of it, you can say, well, statistically speaking, it's predictable. Like, I don't know exactly what's going to happen on any example, but I know the general likely sort of outcome set that we're likely to see. It can be obvious and it can be not obvious. And that's why nothing beats a causal explanation. That's where the data understanding still comes in, and why data preparation is difficult, and why explaining results is important, and why you shouldn't trust a p-value in a newspaper article. And I'm assuming that laughter is that, yeah, we wouldn't have anyway laughed, but you really shouldn't trust a p-value, even in a research paper. Like, people can do a lot to obtain the p-value that they need in order to get the publication that they want. And I'm not even saying that they're trying to do anything wrong as such. I'm just saying, like, it's not necessarily going to tell you whether it solves the problem you really expect it to solve. Because in order to improve your p-value, like, you know, how significant your finding is, you might in fact be doing, like, well, reducing some tolerance around the scale of the thing that you're trying to find at the same time. So there's a kind of a relationship there between, like, the reliability of your result versus, like, the scale or importance of the result that you're trying to find. And it's often possible to trade those two things off. An example of that is weather forecasting. If I want to forecast the weather plus or minus, say, 15 degrees Celsius, I can achieve a far higher, you know, reliability rating than if I want to get a temperature forecast of, say, plus or minus 0.1 of a degree. Neither of those answers will be a lie. And perhaps if you're producing drink bottles, you know, you really are quite comfortable if it gets 15 degrees hotter or colder, and you're very happy with that number. But if you're trying to, you know, work out how long some ice is going to take to melt or something, you probably really care a lot about that difference. So the semantics behind it all, you don't really quite get away from it. But if you can define your problem in a way that you really do only care about one number, you can use the optimization techniques very effectively. And all of that is the same as saying break the problem down, understand the problem. The human understanding doesn't go away. Solving new problems. I don't know whether anyone's got any data sets that are kind of handily pre-organized, but if they do, it'd be cool to hear about anyone who tries some of this stuff. Feel free to email me and tweet me about if you decide to take any of this and do anything with it, and if it's on GitHub, I'll check it out and take a look at it because it's cool. So one approach is to translate your problem to another pre-existing known problem to compare performance against that. So classical computer science, halting NP complete problem definition approach. If my algorithm is incredibly slow with very poor performance, and I can prove that I can translate my problem into another pre-existing known solution that also has terrible performance, then I can claim it's not my fault that the performance is terrible. So there's the arse covering approach aspect of it, but then there's, like, realistically, have I got as good as I can get? How am I doing against similar problems that exist? As I said, baseline against a random forest. Pay attention to input data biases. This is a terribly, terribly important thing to say. I mean, like, many academic studies are based on university people participating in those studies, because when you're a researcher with no money, all of the friends that you can cajole into undertaking your research trial are your mates at university, and you get an unrepresentative set of results coming from that. Pardon me. Look, there are a million examples. Like one of it is, for example, slow trends over time. You might need to detrend your data. So for example, if you have a winter-summer relationship going on, rather than trying to use a full year's data, you might go, well, I'm going to have effectively a bias that changes over winter and summer, and rather than make it part of the model, I'm going to make it part of the data pre-processing. So for example, in winter, I'm going to add 10 degrees, in summer, I'm going to subtract 10 degrees, and then predict that, and then add that difference back in afterwards, so that the model doesn't have to account for that effect, even though you do. And that can, for example, allow you to use data from more different sources if you can actually account for the known differences between those sources. So there are things you can do and things you can trip up on quite a lot. You need to properly evaluate the meaning of a result, because otherwise it's going to turn out to be unreliable in future, and you should definitely visualize everything. So directions in data science, those are just a bunch of cool things. So adversarial example, I've got them out of order. So deep dreaming's is effectively a weights visualization on a neural network. So people have probably all heard about deep dreaming. It just makes these really cool images with this one like a Van Gogh kind of a thing. This one is the puppy dog visualizer. So basically they just take a neural network, train it to recognize puppy dogs, and then run it over all kinds of input and just visualize the intermediate stages. So this is effectively resolving the values of intermediate stages, trying to find puppy dogs in whatever the original image was. And I don't know how much meaning to draw from it, but it's kind of cool. Okay, adversarial examples are really interesting. So what we have here is the image on the left, the image on the right, and I think the thing in the middle is the difference. So what they've done is they have taken a neural network, effectively trained it on the thing on the left, and then modified it as little as possible using an image processing technique to degrade the performance of the neural network as much as possible. And so the image on the left is correctly recognized as, for example, yellow truck, and the image on the right is incorrectly classified. So the human eye just goes yellow truck, yellow truck. But it is possible to fool an algorithm. So one of the things here is you go, yeah, fantastic. I like 98% accuracy, and I've got test data, and it's just all fantastic. Yet, really, you trust you can generalize it? Because these two images here can fool the same network. Now, so some people regard this as a fundamental challenge to whether the networks are learning something true about the data, or whether there's some really big gaps to whether they're going to generalize and handle future examples. Others just fold this into the data preparation. So what they would do is they would just take an image and they would just train it on both the image on the left and on the right, and a whole range of other image modifications. So they would go, well, I want this network to perform whether it's yellow or red or blue or grayscale or skewed a bit this way, skewed a bit that way, intensity, they want to change the intensity, and they will just train the neural network on all of those examples. And so that's called data augmentation. That's quite a powerful technique. But I think it's pretty amazing that you can have a successful network that's easily fooled. Even if you can account for it, I think it's an interesting thing. So this lecture series here is probably the one that I found the best. I think this link just goes randomly to halfway through it, because the first few lectures I found less good, but it was quite a good explanation. And in the repository as well, I've checked out a few papers and links and things like that for further reading. And that's everything I came prepared with. So we can wrap up with a few questions. So we've got 10 minutes, I guess. So is there anything from the audience?
Just something I was going to add with the visualization. There's a Python library called Bokeh, I think, B-O-K-E-H, which makes really sort of slick, explorable D3 style graphs, which just generally makes whatever you produce be worth more money to managers.
You bet. There's a couple of cool things out there. So there's that one that I've used a small amount. There's another one called Plotly, this is kind of like one of these as a service type arrangements, but they just look really nice as well, and it's hard to forego the shininess for the freedom sometimes. So that's quite a nice one. And there's another online web service called Popperly, which is kind of like a spreadsheet graph making thing where you sort of upload CSV data, and it gives you a very easy kind of point and click, choose a column to graph kind of data exploring experience. I don't think you'd ever base like a system off it, but it's not a bad way to just like, if you're not really confident making visualizations in Python for some reason, it's a good way just to throw some data at it, particularly if you want to give some to a manager or to someone else to just, if they're not really a programming expert, it's quite convenient. The IPython notebook is a fantastic way both of developing and sharing things. And I must stop calling it the IPython notebook. It rebranded itself ages ago to the Jupyter Notebook because it runs both Julia and R and probably some other languages as well. So the R is a huge statistical community, so I should really use the new name, but it's just burnt into my brain as the IPython Notebook, so I just make the mistake every time. But that's well worth doing. If you install one in your organization, think about the security of it, please. Because you are giving people the ability to run code on your machine. If you run it on your own machine, by default, you can't connect from off the machine, so it's sort of pretty good as a personal environment. I don't think you need to feel worried about it too much from that perspective, but if you're looking at making a deployment for others, the ways to do it are roughly, well, the notebook carries the notebook output in its format, so you can use both GitHub and GitLab will render those uploaded artifacts, including things like images and cell outputs and things like that. So if you have a kind of static result you want to share with people, if you put it in one of those environments, you can get a reasonably attractive rendering of what's going on. You can embed a bunch of like leaflet and Google Map style displays into the things as well. So you've got quite a lot of rich GUI stuff you can embed into an IPython notebook if you really want to, with sliders and buttons and things like that. A lot of examples on the web.
So first, thanks for making all this stuff available and having all the links and everything. It's awesome. I highly recommend everyone go through all the chapters of neural networks and deep learning.com. So one of the things I've been playing around with is I'm getting obsessed with the departure from accurate neural net modeling as I know it, like as in wetware, because I did psychology before I did computer science. And so I've been doing some experiments. One of the things I've been doing is working on neural atrophy and getting some great results. I've actually got results. The next thing I've moved on to is this, why don't we have resting state? Because resting state is what we see in the brain. And also combining a little bit of random firing. My hypothesis is that the problem with those adversarial images is that there is nothing to shake out the wrong impression. And a shakeout is what happens when you get a random firing in the brain. So I'm not very good at the software, and I can kind of get there, and it takes me a very long time, but I'd love to be able to put up a kind of a result sometime to show that my hunch is right. I've proven the hunch, so if you atrophy your neural network, just like a human brain, and model it on the human brain from first principles, your neural nets will be more efficient, use less memory. They won't be faster, but they'll use less memory and get exactly the same accuracy.
So would you say that atrophy is similar in concept to the dropout?
I don't think it is, because dropout is random, isn't it?
Yeah.
Atrophy, what I was doing is, in the first 500 samples of NMIST, I was seeing if the neuron hasn't been excited at all, then in biology it would atrophy. You'd go blind. If you put blinkers on a child, don't put blinkers on a child. Put blinkers on a kitten. No, don't put them there. You'll actually atrophy the brain part that actually sees that part. So my hypothesis was, well, why not do that in the real model? When I did that, I didn't get a better result in the end, but I used less resources to get exactly the same accuracy. Well, as far as I could tell by doing multiple runs.
Yeah. And
so it's kind of inspired me now to go back and think about all the things I learned when I learned about the wetware neurology. I think I understand why a sigmoid function works like it does, and I've studied in quite some detail. Visual systems a lot. So yeah.
One of the other interesting things along the same vein is like, obviously the human brain is very general purpose. So we reuse the same neural network for many different problem domains. Usually the networks would be specific purpose. Even something like Watson is not in fact a general purpose neural network. It is trained on a very specific data input from which you want to recognize future examples. It's not just like trained on like Wikipedia and all of the age and the known universe and your examples. No, you get, as far as I can tell, you get the performance out of it by restricting the input data set to things that you care about, and it's enormously sensitive to data cleaning. So the ability to recognize relevance and irrelevance and go that whole extra level, I think, is still not there, even on the very large, very capable systems. But I'm much more curious than I am expert. So please definitely don't assume that I'm just absolutely right about all of this stuff. I just feel like it's still valuable to show up and show what results I have been able to achieve.
Also, I very highly encourage everyone to look at the last, say, 100 examples that you don't get when you go right at the top of the neural net's deep learning thing. Have a look at the actual images. You will never guess the 5 is a 5. There's a perfect 0, right? A 0 is a circle, and that's classified as a 1. There's a very, very clear 7 that's like a 8 or something. And it's when you see the error cases, you will basically almost confirm for yourself that what you get with the end result, with the convolutional network, is 100% accuracy. Because the missing cases are, I think, just pure and simple misclassifications.
That's right. Actually, a really similar thing is if you have any kind of expert system, experts will also only have a certain % accuracy. So comparing expert agreement is really interesting. So if a human goes through and says these are all similar, you really might want 10 people to all do that, and then your predictive accuracy might only need to be as good as the collection of human accuracy, because there's not in fact perfect agreement about what's one thing or another. So again, the details of what you're checking against are relevant. Well, I'm beginning to get timeout warnings and things like that. So
there's still a couple of minutes.
Still a couple of minutes. Yep.
Questions? No?
I think we've done it. All right. Thanks very much, everyone.